In this video, we're going to look at probabilities involving union and intersections. A single card is drawn at random from a deck of 52 cards. Determine the following probabilities. Enter your final answers as reduced fractions or whole numbers. And we're told, note, aces are not considered face cards or number cards. So this is the first video with a deck of cards in it, so let's just talk about it because we'll be using this a lot in probability. There are 52 cards in a deck. Okay, we have 4 suits. These are our suits: clubs and spades, hearts and diamonds. Clubs and spades are black, hearts and diamonds are red. Okay, then we also have what we call the rank, and that's a ranking is how high or low a card is. Okay, so here we have kings high, then queens, jacks, and then 10 all the way down to 2. Notice we have ace here. Ace is sometimes considered low, and sometimes it's considered high. So here we have ace is low because it's all the way on the right. We won't be using aces in that way as low or high, but notice we're saying here they're not considered face or number cards. So we'll be using that in probabilities a lot, so we'll exclude aces from those. Okay, so let's look at, there's 3 groups of questions. Let's look at the first group, Group A. So first we're asked, what is the probability that a card drawn is a 5? Okay, so I'm going to highlight the 5s. And notice there are 4 5s. There's 1 5 for every suit. Okay, so there's 4 out of 52 5s. Okay. Now, something that'll be helpful to note, you can always simplify these on your calculator, but it's handy to note that 52 is divisible by, if you need to simplify, 2, 4, and 13. Okay, so 4 is divisible by 4. It turns out 52 is also. That may not be a number fact, you know. But an easier way to remember, if you start to look at the structure of a deck of cards, it's set up this way for a particular reason. Notice we have 1 column of 5s, and there's a total of 13 columns. Okay, so this would be, since all of the columns are equal, this would be 1 out of 13 equal columns, which gives us 1/13. Okay, so you could remember to divide the top and bottom by 4, or you could use some of these patterns to help you. Let's look at the next one. What is the probability the card is a queen? Okay, well, here are the queens. And again, just like the 5s, there's 4 of them. So we have 4 out of 52, which again simplifies to 1 out of 13. Next, we're asked, what is the probability the card drawn is a 5 and a queen? So remember, and means intersection. But notice these 2 columns don't overlap. Okay, we would say that being a 5 and a queen is mutually exclusive. You can't be both a 5 and a queen. Okay, or in terms of probability, we could think, well, we know the denominator is 15 or 52, sorry. How many cards are both 5s and queens? Well, that's 0. So 0 out of 52 is 0. So it's impossible to get a card that's both a 5 and a queen. And lastly, what is the probability that the card drawn is a 5 or a queen? Well, or means a 5, a queen, or both. Now, we know a card can't be both, but we do have 5s and queens. Okay. So notice we can count these. There's 4 and 4, which is 8. Okay, notice that's the sum of the denominators here. There's 8 in total out of 52. And now we can divide the top and bottom by 4, or notice we have 2 out of 13 columns, so this simplifies to 2/13. Let's look at the next group. Okay, here the first thing we're asked is to find the probability the card drawn is a face card. So face cards are kings, queens, and jacks. So I am going to highlight these with a yellow highlighter. Okay. There's 3 for each of the 4 suits, so there's 12 in total. So the probability of a face card is 12 out of 52. or also notice it's 3 out of 13 columns. So if you divide the numerator and denominator by 4, you'll get 3 out of 13. Next, we're asked, what is the probability the card drawn is a heart? Well, here are the hearts. There's one row of hearts. And notice that there's a total of 13 hearts. So we have 13 out of 52. And remember I said 52 is divisible by 13. So we could divide these both by 13. But now if we look at this chart in a different way, notice there's 1, 2, 3, 4 columns that each have the same amount of elements. We have one of the columns. So this is going to simplify to 1/4. Next, we're asked, what is the probability the card drawn is a face card and a heart? Okay. Well, now in this case, we do have some cards that are both face cards and hearts, namely King of Hearts, Queen of Hearts, Jack of Hearts. Okay. So let's just connect this to Venn diagrams real quick. If we had our face cards, is this set. This set is hearts. Okay, and then we have a universe. The intersection, face cards and hearts, has 3 elements. Okay. Only face cards would be these 6 and these 3, not including those. So we'd have 9 face cards. And hearts that are not face cards, well, that would be these 10. And we could figure out what goes out here, but I don't feel like counting it. We just need these numbers. Okay, so we have that face card and a heart. There are 3 such elements. So this is 3 out of 52. And this cannot be simplified. 3 isn't divisible by 2, 4, or 13. Now finally, what is the probability the card drawn is a face card or a heart? Okay, so now we have or, which is intersection. Which is union. Okay, we just did intersection. Okay, so we could look at the disjoint pieces here of the Venn diagram. So it's going to be 9 plus 3 plus 10, which is 22. Let's look at this diagram as well. This kind of looks like a Venn diagram. It just is rectangles and overlaps differently. Okay, well, what if we started with the face cards? We'd have 12. Okay, that would include these 3. If we added the number of hearts, well, that's 13. So we'd add 12 and 13. But notice we'd be counting that middle part twice. We counted these 3 cards twice. So we'd have to subtract that off once, okay, because we only want to include those once. Okay, so when we have the disjoint Venn diagram, we can add these directly, and we get 22 over 52, which simplifies to 11 over 26. Okay, or if we don't want to go through all the trouble of the Venn diagram, we could add the 12 and 13. Okay, note that we had the intersection twice, so we could subtract that off. And that will give us 25 minus 3, which is 22 over the denominator, the size of the sample space. Okay, so that's going to be our big idea. In the next problem, we're going to generalize that. Now we have group C, which is really just one question more than a group. It says, so there's some notation in here, don't let it frighten you. Let E1 and E2 be 2 events for an experiment. So in the last examples in Group A and Group B, we drew a card. Event E1 for the first one was, I think, drawing a 5 or drawing a queen was E2. For Group B, our first event was drawing a face card, and E2 was drawing a heart. Okay, so that's all these are. It's just a generalized version of that. And it says determine a formula for the probability of E1 or E2. Okay, so that's the union based on the problems in groups A and B. So I've written our results, and we started discussing this in the last problem, at the end of the last problem. Okay, so notice that here we found that the intersection of E1 and E2 was empty because a card couldn't be both a 5 and a queen. Okay, and notice if we add the 4 plus 4, we get 8. Okay, so if we want, oh, I wanted the red, sorry, I want a red pen for this. If we want probability of E1 or E2, it equals the probability of E1 plus the probability of E2. Now this part is going to seem weird, but it's going to help us connect these two groups of problems that were different. We can subtract off the intersection. Notice the intersection was the empty set. They didn't have anything in common. So it's okay to subtract it off. And we know we will get the probability of E1 or E2. So this in numbers was 4 out of 52 plus 4 out of 52 minus 0 out of 52 equals 8 out of 52, where 8 out of 52 is the union. Okay, let's see how this applies to this problem. Okay, so we had a little more space here. If we had, oh, that's horrifying, hold on. So if we have the 12 out of 52, so the probability of E1 plus the probability of E2, and then we subtract off the intersection because we said we counted that both here and here, we get the probability of the union. Okay, again, 25 minus 3 is 22. Okay, so this is our general result. Okay, so note here you may do some problems and just say, oh, I have an OR problem. I add the probabilities. And that will work as long as the intersection is empty. But this formula we're going to write here, if you always remember subtract off the intersection, then no matter whether they're mutually exclusive or not, our formula works. So let's write this here. Probability of E1 or E2 equals the probability of E1 plus the probability of E2 minus the probability of E1 and E2. Okay, so just subtract off the intersection. And this is our result in general that works for the union of any two events.